on so your friends can follow up. Okay.
Yeah, sure.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So
Waalaikumsalam.
today we will cover about how we can do the facility layout evaluation, how we can evaluate the layout that we already proposed and that we already built by having the both qualitative and then the quantitative method. Okay, so for today's lecture, we will cover this. So we can do the layout evaluation by having the data of the load or frequency and then the distance if we have those, and then calculating the cost for the material movement. And we also can do it through the qualitative methodology by having the ARC as the base and then the adjacency status for the facility. So when we talk about the facility layout, there are two types of layout. It can be a machinery layout, which if we talk about the within department one, and also we can talk about the department layout if we talk about the overall facility. So either way, the concept are the same, and how we calculate and how we evaluate is also the same. Probably the difference will be what kind of facility or what kind of entity that we try to calculate, right? When we talk about the machine layout, then we talk about the relationship between each activity that happen inside or within department, how each material is flowing from one machine to another, from maybe workstation to another workstation. While if we talk about the department layout, then we also need to consider the type of the machinery layout, the type of the process that we use. So if it's fixed product layout, then maybe we need to consider that some locations are fixed. While if we consider the product layout, then we know that some machine needs to be adjacent to each other. While if we talk about the process layout, we probably talk about the flow pattern between one department to another department due to different types of product. And to build the initial layout, we have learned about the ARC or the activity relation chart. So if you find in another literature, they call it REL chart or relationship chart. It's the same with the activity relationship chart or ARC. While for the ARC, it's sometimes they call it the activity. For REL chart, it can be flow or the other thing. And then last week, 2 weeks ago, we learned about the from to chart. And then today we will learn a bit about how we actually can build the from to chart, and then understand how we can calculate the layout for our the score for our layout. So just a glimpse. The from to chart itself is a matrix, basically a symmetric one, that show the material flow from activity I to J, from one activity to other activity. It can be from one department to another department. It can be from one machine to another machine. It can be from workstation to another station. And from to chart, we actually can build several type of from to chart, several type of machine. So there can be a load from to chart, which is actually the material flow. And we can also have the distance from to chart, a matrix that show the difference from one department to another department, or distance metric. And we can have the so-called load distance model, which basically try to calculate the layout itself. So by having the load or frequency and multiply it with the distance, we can find the overall total score for our layout. So the bigger it is, then it means that the layout should be improved, because the objective of this model is to minimize the total unit distance travel. It means the bigger the value, the layout is not good, because the material handling is still quite large or a lot. So when we calculate this load distance model, basically the basic is to calculate the basic idea is to calculate the cost for material movement. So let's say we have several activity inside the facility, let's say the number of M facility, and then we will have what we have here, which is the load. One is the flow volume between one activity to another facility, and then we have dig, which is the distance between one activity to another. And also, if it's possible, sometimes a company industry also have the calculated cost per move between one activity to another activity per unit distance. So to calculate the cost of material movement, we basically just multiplying all the factors, which is the the flow, and then the costs for material handling, and also distance. In some cases, the load distance model can also ignore the cost and just say that the cost is equal to 1, because sometimes it's quite difficult to actually find the value of the cost for material handler. Unless you have the data, unless you already have the calculation per meter, then maybe we can use it for evaluating the layout. So in this case, we can say that we try to minimize not the total cost, but total travel distance. So it means that we can just make it like this, Fij and Dij. So this is actually enough to evaluate the model, and we will focus on that today in the load distance model. So this is the example. Let's say we have A, B, C, D, and E location. So it means we have, this one is cannot be changed. So we have, let's say, 5 rooms, and then we have 5 work center, 1, 2, 3, 4, 5. And our job is to assign this work center in the dedicated location, A, B, C, D, E, so that we can minimize the total travel distance. So for example, in this case, we just randomly do the what is that, the layout. So for example, this is maybe more easier for you to understand. A, B, C, D, and E. And then it means that this is 1, 2, 3, 4, 5. So I assign 1 to location A, 2 workstation 2 to location B, 3 to location D, and so on. And from there, we develop the distance metric, which means it's the distance that must be traveled between all the area. So in the from to chart 1, I mentioned that it basically asymmetric, but when we talk about distance metric, it's commonly is symmetric, because the distance will not change from one location to another unless we have or we use a different type of material handler. For example, when we use a conveyor from A to B, while there is no conveyor from B to A, then maybe it's gonna be asymmetric. But commonly, the metric is symmetric. So for example, we build from one location to another, as just check it like A and B. This is the location one. And then we build the load matrix or the from to chart material flow. So for example, before I mentioned that the arrangement for the workstation is 1, 2, 3, 4, 5. So we make it 1, 2, 3, 4, 5 according to how they assign to the workstation. the sequence. So for example, there are a number of units that being moved. So in this case, we use the number of unit. You can use the number of frequency. You can use also if you move the goods in batches, or you can use the weight for the total weight that is being transferred from one location to another. So from there, we develop the load distance metric by basically just multiplying these distance metrics and load metrics. You need to make attention to this, because for this one, the location, the from to the load metrics and the load distance metric should be, how to say, should be same with how we assigned it. So for example, this A, B, C, D, E, right, before. So the sequence should be A, B, C, D, E. So does the sequence for the load metrics. And then we can calculate the distance, load distance metric for layout one. This is the example. Just calculate it and then sum everything. So as I mentioned before, you just Fij multiply by Dij. So you got this. Okay, so the question will be, is the layout one is the best layout? Because when we talk about this, there will be a number of possibility, right? So when we have 5 locations, 5 workstations, then we have roughly 5 factorial possibility, which makes it around 120 possible assignment. And then what can we do then? Then probably what we can do is doing either trial and error, or do other things. So for example, the other layout, that the other proposed layout is layout, we call it layout 2, where workstation 1 is being assigned to A, workstation B, workstation 4 is assigned to B, C to 5 to C, 3 to D, 2 to E, and then we call it layout 2. So then we make another, before we have distance metric, we use the same distance metric, right? A, B, C, D, E. And then we can make another load metric. This time it become 1, 4, 5, 3, and 2. 1, 4, 5, 3, and 2. And just multiply this one and become the load distance metric for layout 2. So after that, again, we sum everything, and then we got this much. So we can see that compared to layout 1 here, 23,000, and layout 3, layout 3, layout 2, layout 2 have a better score compared to layout 1. And because we cannot just do it randomly, there is a possibility that we use a certain groups, which is a better approach, easier approach, where basically you can assign work center with large unit flow rates as close as possible. So for example, if we can see here, for example, where is this? 1 and 4 should be close, for example, and 1 and 5 should be close, and then 1 should be close to 2. So the location can be checked by the number of load if we only consider this heuristic. And you can basically assign work center with the small unit flow as distance as possible. And then if you have time, then you can do trial and error, but then it become a bit ineffective, because this time we talk about 5 location with 5 work center, which makes it like 5 factorial, but additional workstation which will make it like 6 factorial, and it's become quite difficult to solve. So in that case, later on, I will explain about how we can do it in a better way. So how we actually construct or find the load matrix. So for example, we have this time we have 5 jobs. This is, I will explain how we can make the load matrix if we only have the sequence and number and then the total product that they need. So for example, for this one, we have 5 jobs. Job 1 with the load 100, job 2 with 200, job 3 with 300, and etc. And then they need to go to 6 work center, 6 machine. So A, B, C, D, E, F, and F. This notation A, B, C, D, E, F is different with the location. Yeah, this is just the notation for the machine that they need to go. So for example, job 1 go from A, then B, then C, then A, then C, then D, and etc. And then job 2 from CA and to B and B. So this is the sequence. You already made it. You already have it in the OPC, if I am not mistaken. So from there, we actually can build the load by having this from to location. Yeah. So for example, we first calculate the A to B. So this should be, sorry, this should be 300. This should be 0, sorry. So it should be like this. It should be 0 0 0 0 from A to A, B to B, and then we check A to B first. So A to B will be 100 plus 200 plus 300 plus 150. Okay, so 100, 200, 300, 150, 700, 750. Then we can have A to C. Do we have A to C? Okay, here A to C is 100 plus 50. So it makes it 150. And do we have A to D? No. Do we have A to E? I don't think so. And do we have A to F? No. And then we keep continue by having the B to A, for example. So we have 300 plus 50, so 350, and then so on. So until we get the full load matrix. And how we actually can calculate the distance measurement from one location to another location. There are several ways to calculate it, and it depends on which approach you try to you have. So for example, there are, in this case, I will explain 3 types of distance measure. The first one is the rectilinear distance, where you basically and find the centroid for the location first, and then you calculate this distance from one coordinate, centroid coordinate, to another centroid coordinate. So in this rectilinear distance, you just make the kind of like straight line according to these coordinates. So it means that for this one, the distance travel is calculated by having the vertical, both vertical and horizontal distance. And then, for example, this is the location and this is the other location. So if this is, let's say, this is 100, 100, and this one is 400, 400, then the distance from location X to location BI will be 100 minus 400 absolute, which is 300 plus 300. So it's 600. So it's like 300 plus 300. Okay. So the second one is the Euclidean distance, where you basically try to make the straight line directly, diagonally from one location to another. So we can see here that it means that you cut lots of distance by calculating the Euclidean. So it's more like a kind of like Pythagoras, where you find the location from one to another, and then you get the straight line diagonally. And then This is the formula. You can just use it. And then there's the Chebyshev distance, where you try to find which is the maximum distance between the movement from x coordinate and y coordinate. So first you find the the distance in x coordinate and y coordinate. So for example, let's say in this case this is the same, yeah, the value. Let's say in this case it's 100, then this is 300 and 400. Sorry, 400 and 300. So it means the dxbi will be the maximum between 300 and 200. So they choose 300. So there are three types. Which one is more, how to say, realistic? Then probably we can use the rectilinear. Or if you have the real, how to say, distance, so you basically calculate it manually, then it's also possible to just make the from to chart distance from to chart from that data. So how can we evaluate our layout based on the qualitative measurement? So we already developed the ARC, or activity relationship chart, or I can call it REL chart, where we have this a rating or closeness rating or closeness value. It can be A, E, I, O, U, and it should be X. And it is ordinal value, right? So there is no numerical value there. And we can transform those value, those absolutely important, especially important, ordinary important, unimportant, and undesirable into the cardinal value by assigning the subjective value one. So before RIJ is the closeness rating, then we have FRIJ, which is the value for those closeness rating. And because this value is quite subjective, so you can actually assign any kind of value. Sometimes it can be big, sometimes it can be have a big gap, but this value just mentioning, how to say that, become a representative on how important this closeness rating are. So then aside from ARC, we need the detailed data for adjacency. So when we do call the layout or workshop adjacent, if they share a common border in a positive length, it means it's not just a point. So we call it fully adjacent. If it's only the partially adjacent, then maybe they share one or a finite number of points. And if it's not adjacent, it means that they don't share anything, even a point. So for example, this is the case. We have a 5 workstation where and we build the layout like this. So what makes it fully adjacent? If they are sharing a common border, it means 1 and 2 are adjacent, 1 and 3 is adjacent, 3 and 4 is adjacent, 2 and 4 adjacent, and 4 and 5 is adjacent. So they have the adjacency value equals to 1. So this is the coefficient, yeah. And then we can have a partially adjacent. It means they share one or a finite numbers of points. So for example, in this case, 1 and 4 is partially adjacent, 2 and 3 is partially adjacent, and 2 and 5 is partially adjacent. And usually we give a value of alpha. So later on, we will try to give it a value, but usually alpha can be changed accordingly. So it can be value from more than 0 but less than 1. So it's between 0 and 1. And we have the non-adjacent workstation. For example, 1 and 5 are not adjacent to each other. Something like that. So, and how we can calculate the layout score based on the adjacency. So we have the VRIJ before, right? Which is the cardinal, the value for the closeness rating. And we have the coefficient for AIJ. And we try to maximize this layout score. So your layout qualitatively is better if you have a big value for this LSA or the layout score based on adjacency. How we make the value for this one is depends. So for example, it's really important. So we just give a big value, something like this. To ensure that, so for example, I will give undesirable the minus value to ensure that the workstation that should not be adjacent. No. So that the workstation or department that should not be close to each other are not adjacent to each other. So I give it a really small value. And on contrary, I give a really big value for the absolutely important. So to ensure that this A rating between department, for example, X and Y are adjacent to each other, something like that. So this is how we do this. And then the next one will be this. So we got the layout score qualitatively and quantitatively. And then how can we try to improve that if we find out that our score, I think the score is really big for the load metric distance, or I think the score for the adjacency is quite small compared to what I expected. So we can have several heuristic or algorithm to help us to either constructing from beginning or improving what we already have, the initial one. So when we have the real problem here, like facility layout, we try to make the model, right? Then we try to find the correct algorithm to solve the model and then make adjustments so that we can implement it. And prior to that, before I already explained about from the chart, the ARC, and how we can calculate the layout score. And today we will talk about this, how we can make the construction and improving the layout, how we can construct the layout and also improve the layout. So we can, I will explain 3 different algorithms, which is by definition is a procedure to find the solution by having a finite number of steps. And we can code this algorithm into computer so that it can solve faster. But we can, if the number of the scale problem is quite small, then we can use this algorithm manually, calculate manually. So the difference, there are 2 types of algorithm, the optimal one and heuristic algorithm. You can use the optimal one, basically doing all the possible solution, which take a lot of memory. And because this facility layout, as I mentioned before, even one additional workstation and one additional location can add up to like how many? So if 5 factorial is 120. If we add one more workstation, it becomes 720, which means it's non-polynomial problem. Its computational time will increase exponentially. So our brain will not be able to cope with that. And even the computer have a memory that is limited. So we sometimes for big case problem, we just use computer. So there are different type of heuristic algorithms. Today we will talk about that. There are one that is a construction algorithm. Construction means that you generate the facility from the scratch. There is the modified spanning tree. There are correlate, and another one that I will explain today is the ALDEM. And there is the improvement algorithm, which basically systematically modify the starting solution. What that means is that because we have already initial solution, we can modify any solution so that we can have a better result. There are 2 OPT, 3 OPT, and graph. And today we will talk about graph. And there is another one. They mention it as a hybrid algorithm where they can use both as constructive and also the improvement algorithm, which is block plan. So for today, we will talk only 3: correlate, ALDEP, and graph. These 3 and block plan actually the one that developed this algorithm have made the kind of like software, so you can actually try to find it on internet, but I'm not sure whether they are free or not. Maybe you can try, and if you have it and can run in your computer, maybe you can like do a bit, and maybe you can use it for your project. So for the modified spanning tree is being used for single row layout problem. What is single row layout problem? It means that there is only single row, something like this. So we have A, location A, B, C, D, E. And then we have 1, 2, 3, 4, 5 workstation, and we need to assign one by one. Okay, so in this case, the shape might be similar, for the department might be different. So it can be any case, but it's always single row. So the MST try to minimize the overall flow multiplied by distance, which is the same with the load distance one. And then they use the same type of heuristic logic, where the pair of machine or pair of workstation with the large flow is being placed adjacently. So if we return back to the material that I mentioned before, they have the heuristic rule where the large flow value should be placed close to each other. However, sometimes it cannot be optimal because the non-adjacent weights are ignored. So for correlate, it's used for single story layout problem. The shape are kind of like rectangular or square. It can be both, and it can be for several or multi row. And then we use the value from the ARC and then turn it into the quantitative data by having this TCR, or total closeness rating. What is this? Is the value that I mentioned before about where the value of the closeness rating is changed into a number or quantitative data. So the algorithm for correlate is quite easy, where they calculate the TCR first and then place in the center, and then they add the facility one by one based on their level of interaction. So the third one will be graph, and graph can be used for the almost the same like the correlate. It's a single story layout, and it can be used for multi-row layout problem. However, as graph is an improvement algorithm, you will need initial layout as input. And then how graph works is by exchanging the location of here adjacent pair of the facility, and then the the pair exchange, the location exchange that have greatest cost reduction is selected. And the last one, yeah, is a block plan, which can be used for either single story or multi-story layout problem. However, it's it's being used for a small problem, up to only 18 facility, and it has a both constructive and improvement algorithm, which can handle both quantitative and qualitative. So, or you can use other software like Factory CAD, Plan, and Flow. But I think this is a paid one, paid software. So some of those algorithms have the ARC as the base for them to build the solution. So when we talk about the traditional layout configuration that we already done, you should have submit your work, right? We build the ARC, we build the ARD, then we make the space relationship diagram, and then turned it into a block plan that represent the final layout. Okay, so if we have this kind of ARC, we understand how they have this closeness rating from one department to each other, and how we can build the ARD from there and space relationship diagram, and then we can make the block plan. So block plan is just how we will, so department 5, department 10, department 8 should be close to department 10, department 9 should be close, for example, here. And then department 7 should be close with 9. And then 6 should be close with 7. And then maybe 4 is here. 2 is here. 3 is here. Then you can put 1 here. So this is one of the block plan. And you can also make several alternatives based on the space relationship diagram here. Like 5, 8, 7 maybe here, 9 maybe here, and then this is 6, and then this is 2, and then this is 3, and this is 4, and maybe this is 1. So there are several ways to make it, right? And in hierarchical approach, we make several alternatives. We can calculate it using the way that I already explained to you before, how we can calculate it either by having this load distance metric, or by having the calculation for the layout score based on adjacency. And in manual core lab algorithm, we will do the core lab algorithm manually. We basically use this ARC as the base. And then, as I mentioned before, we actually change it from the qualitative to quantitative, and assign a value for each closeness rating. Then, for each department, we calculate the total closeness rating by summarize the absolute value of the relationship with other department. And how to select the department, which department should be become our initial solution, is that department with the greatest total closeness rating. And if there is a tie axis, then we choose one with more A's, or absolutely important. And make sure that if there is department with X relationship with the first one that we already selected, then you shouldn't choose that in the last layout. And the second department that is being chosen should have the A relationship with the first one. And if a tie exists, choose the one with greatest TCR. So maybe to make it easier, we can try to do it directly with this example. So what you need to understand is that we need to use the concept for the adjacent and fully adjacent and partially adjacent, and have a value for that. So as AIJ or adjacency. If it's if activity I and J are adjacent, usually we give us 1 value. If it's not adjacent, then we give 0. If it's partially adjacent, we give alpha, right? So in this case, the status adjacency is used for the weighted placement. How we can place the department, in which location we should place the department, something like that. So after we first choose the department based on the TCR, we put it in the middle, and then after that we choose another department to be put. And how we select the location is based on the evaluating all possible location using the weighted placement with the greatest weighted placement value. So this is the example for calculation. So let's say there is a closeness value rating like this. If it's absolutely important 125, it's especially important 25, and etc. And if it's partially adjacent, then we give a half score O. And then we transform this ARC into a better like table. So we have department 1 until 9, and we have the relation from one department to another. Then we calculate the TCR. So for example, before it's how many? VA is 125, VE is 25, and I is 5, and 1, and 0, and minus 125, for example, like that. So it means to get this TCR is just multiply by the value. So 3, so it means this one is 325 plus 125 plus 2 plus, okay, so it's 402. And you can calculate it for all. And then we have the TCR, and then we just short it and give the order. So as we can see here, department 7 have the biggest TCR value equal to 1. Equal to 625, and the department 7 is the first one to be placed. So we put it on the block here in the middle. Then we calculate the weighted placement. So before calculating the weighted placement, we have to understand what department should be placed next after department number 7. So we need to find what which department have the A score, A relation with department 7. So it can be department number 9, it can be department number 6, it can be department 5, and it can be department number 4. Then we need to check the order, which one have the greatest TCR. So in this case, department 5 has the better TCR, so we choose department 5 to be the next department to place. So as we can see that department 5 and 7 are absolutely important. So how we can calculate is based on that. So because 5 will be adjacent, this location will be adjacent, so it means that 100 multiplied by 1, because this is adjacent, it means that adjacency status is equal to 1, and this location is 125 multiplied by alpha, which is half, so this is equal to 62.5, and we calculate for all possible location, and then we just place it in either location that you think are appropriate. So for example, in this case, we choose this location to place department number 5. Then we check again which department should be placed after department number 5 by checking this. So for example, 5 have a relationship with 6 and have a relationship with 9, and then we check the TCR, and 9 have a better TCR, so we choose number 9. So then we again calculate this. So as we can see here, this is it means it's adjacent with 5, so it's 105, plus it's partially adjacent with number 7. So how 7 and 9 department relationship is also A. So it's 125 multiplied by half. So it means it's 187.5. And then you calculate again from the other. No problem, no problem. Okay, I record this from the beginning, and then I will share the recording later on, so you can do self-study again. I'm really sorry. And then from this, we choose this location for the department number 9. Choose here. And then again, we keep doing the same. So after number 9, 9 have the absolute important value with number 3. So we choose number 3. And then where should we place the location is by calculating the weighted placement. So as we can see here, so we can find that some value are 0. Maybe if we go to here, 7 and 3 have the U relation, it means unimportant. So the value of either adjacents or partially adjacents are 0. That's why this location are 0. And we could continue until a layout is being established like this. Like this. So this is the final layout. So as we can see here, for the core lab, there the location, the department or the workstation is considered as a block or a square rectangle without considering the shape, the other shape, and etc. And if in other algorithm, there are mostly actually if you realize, they always kind of assume that have assumption that the given space will always be rectangular shape. So this algorithm that I will explain all, and some other algorithm will be have a rectangular shape or have a square shape. And the next algorithm that I will explain is called CRAFT, which is the improvement procedure. So if core lab is a constructing one, so we construct from the scratch. In CRAFT, we already have the initial solution. So this is the example. For example, we already have 4 departments in this 4 location with different shape. Yeah, we have some square, some rectangle, and then the question will be, this is, we call it the initial layout. And then the question will be, is this layout is good enough? And can we improve the layout? Then we can use the CRAFT or computerized relative allocation of facilities technique. So what you need to do first in CRAFT is calculating the distance between 2 departments. And as I explained before, there are several ways to calculate the distance. And in CRAFT, we use the rectilinear path from their centroid. So, for example, we have location 1 and like this. This is A, and then we have probably, let's say here, the location, this is department B, yeah? And then department A have coordinate XA and YA, while the centroid for department B is have coordinate XB and YB like this. So how we find the distance is by calculating the movement from each coordinate. So xi minus xb plus yi plus yb. So this is the distance. So in graph, we use rectilinear. So this is the example. So let's say we try to calculate the distance between department A and C, and we already have the data for the centroid of A and C. So the distance will be 50, 30 minus 80 absolute plus 40. So it means 90. Yeah. So in graph, we try basically in how we try to analyze our layout is based on the total distance traveled. The bigger the total different this total distance, it means the worse the layout. So in graph also, they have such kind of like a logic or a rule where if the number of trips between two departments are very high, they should be placed to each other. Okay, and the total travel distance or the distance itself multiplied by the number of trip or frequency. So if there are many lots of frequency there, then there are many movement, then it means they need to be close to each other. And total distance travel is basically just computing the distance and then multiply by frequency of the movement, then summing up all. So here, so for example, we have this data where there are material handling trips. It means this frequency. And then we have the distance from A to D from all departments. So the total travel distance, it's almost the same with the load distance metric, but this is a frequency multiplied by the distance. So the number of trip, you multiply it by the distance, and then you got this total distance travel by summarize everything. So in this case, for you multiply from AG of the distance and then frequency movement or a trip. Okay, and because you try to minimize, you try to find the smaller number as small as possible. Yeah, and in graph, we try to save as much as possible. It means that because we already have the initial layout, we will try to have a reduction of the total distance travel by having by improve the pairwise, improve the layout by changing a pairwise interchange. How can we compute is this is what you need to understand first. So there are some departments that have a adjacency to each other or interchange. In craft, they call it rather than using adjacent status, they call it as a pairized interchange. It means that they can be changed to each other. And for example, the feasible pair should be adjacent. So A and B can be exchanged. A and D can be exchanged. So and A and C, because they are adjacent, yeah, they can be exchanged. C and D can be exchanged, and B to C can be exchanged. So because B and D are not adjacent, so we are not gonna compute the interchange between B and D. Then we try to compute the all feasible pair, which is AB, AC, AD, BC, and CD. How we compute it is by have a new centroid. So because, for example, so this this should be the initial centroid, right? And then we try to change the department C and D, so it become like this. If it's A, this is B, then C become here and D is here, I think. Yeah, oh sorry, should be like this. This is D, this is C. Okay, so as we see here, the centroid for A and B are not changed, but centroids for C and D are changed. So we need to recalculate this. The distance, the matrix should be changed. And then we multiply it by the handling trip. And when we sum everything and then got the value. Oh, so if we change C and D, then we can save around 160. Then we do all the calculation with A and B, A and C, and B and C, and A and D. Yeah. Okay, so to complete the exercise, yeah. So you need to compute saving for all feasible interchange. But if there is no saving, then stop. If there is no saving, we just assume that it's already optimal. The result is already good. And if you have interchange that gives positive saving, for example, before, if we make movement for C and D, then we save 160. If we move, for example, A and B later on, we got, I think it's 0. And then if we change the B and C, probably we got, for example, 200. So from all the possible pair changing, then we change B and C. Then you implement the change and repeat the above 3 steps until you got no positive stopping again. So that's how you find these optimal solution for craft. So, but sometimes what you need to understand is that the shape might not be, I'll say that, exactly like rectangular or square. So sometimes you will have a peculiar shape like this. And in this case, we need to understand how to calculate the centroid. So in craft, because we use the rectilinear, right? So to find out the distance travel, we have to know the centroid. And in this case, first we need to find the centroid for A by divide the A department into A1 and A2. And then the centroid for X center, yeah. XA will be this, and centroid for YA will be by calculating like this. So for example, this one is, I don't know, 70, 85, 70, 85, right? And then this one is 30 and 60. And the area is 60, A1, the area 1 will be 60 multiplied by 30, which is something like this. So this is, and while this one is 0, 60, like this, yeah, A2. So for XA will be A1 plus divided by 3000, yeah, this one plus this one. So I don't know how much, something like that. Yeah, we can calculate it using like that for Y2. And in regards with craft algorithm, because it's improvement procedure, we have to have initial solution first. It's not construction, it's an improvement. And the bigger the case, then it will take a lot of time to actually calculate it manually, because we need to in every stage we need to calculate the pairwise interchange and then choose the best one. Okay, so don't only the department adjacent to each other is considered as the pairwise interchange. Otherwise, you will just exclude it for the calculation. And then sometimes even after the interchange, you can't find a more saving. So in that case, maybe we can try another pairwise interchange. If all the possible pairwise interchange have a 0 or negative value, it means that the current layout is considered as optimum. And the last algorithm I will explain is ALDEP, which is a construction algorithm. ALDEP is stand for Automated Layout Design Program. So in craft, we require initial layout, while so we basically improve. In ALDEP, it's almost the same with the core lab. Well, we did not need initial layout, and then make the layout from scratch. What kind of data we need is the data about the size of the facility, the number of departments, size of department, and also ARC. We also need a sweep wind, and I will explain it later while we constructing the layout using this ALDEP. So in ALDEP, almost the same with the core lab, we basically make a kind of like a block in a blocks. So in core lab, one department is represented in one block, but in ALDEP, a department is represented by a several block based on the size of the department. So for example, here we have 8. The space availability is 8. This is 8, this is 6, and then we have 6 departments that we need to arrange, with each department have dedicated numbers of a space. And as the initial one data, we need the ARC, and then we have the value, yeah, closeness rating. And in ALDEP, this ARC, almost like the core lab, becomes the base for developing this layout. The difference is in the core lab, we know that we have to calculate the total closeness rating first to find the first department to be put in the middle, while in ALDEP, the placement start from here, the upper left corner, and which department should be choose is random. So you can choose any department you want to start the layout. However, this become a kind of like disadvantage for ALDEP because we choose the department randomly for the initial one. There will be several alternatives for layout. While in core lab, because we use the value of TCR, there won't be any problem, and you will construct only one solution. So let's say here, for the example, we choose the dock room, or we represent as D, yeah, and the dock room have needs 8 blocks. Okay, so while we try to put it here, then we also can decide the sweep wind, which is the wind and number of the blocks, the width, yeah. So you can choose 2, you can choose 3, you can choose 4, you can choose 1. So in this case, for example, I choose 2, and then we just place 2 here, dock. And once you decide the wind as 2, the other department should follow it. So let's say we place the dog room already, then we need to find the next room that have the proximity rating A with dog. So which one is a storage? Okay, so storage become the second department to be allocated. Storage needs also needs A, and then because we already decided the two, so it's like this, 2, 2, then they need to be clustered together. So the possibility is like here. Okay, and then here, see, yeah, see carefully that the allocation start from upper left, and because we have decided the width as the width is 2 blocks, then we need to follow the pattern. Okay, this zigzag pattern will continue to be followed by another department. So the next one, we should check again the ARC and find which department have a higher proximity rating with storage. So storage has A with production, so we choose the production here. Production needs 14 blocks, so again we put it in a 2 blocks like this, 2, 2, 2, 2, 2, 2, until we got we finish everything, and then it keep continue until all the blocks locate. So let's check again, because after the production area, then we have T, which is tool room, and after tool room here, tool room, okay, there are two that is not located yet, which is the locker room and office room, and they have different rating. So what happens if there is a tie? Basically, again, this is gonna be a disadvantage for our debt, because you can just choose it randomly. Okay, so after choose it randomly, let's say let's choose locker room, then put it here 2, 2, and then you have the last one, which is office. And we finish arrange the laptop. Okay, what's gonna be a problem is when we do the score evaluation. So the score evaluation will be to find the value of rating, Bij, yeah, multiplied by adjacency, right? For activity I to J. So what happened if the value X is located one to another? Yeah, we can check here. So for example, first we compute the overall rating, yeah, and then we need to understand this. Sorry, this is slide 50. And then we find the adjacent department. So for example, this one, DNS are adjacent, S and P adjacent, DNP adjacent, PNO yes, PNT yes, PNS yes, S to L yes, L to O, L to T, P to T, so and etc. So you list all the adjacent department. It means that it's equal to 1. Okay, I haven't changed this. So the numeric score is 57, yeah. Okay, so for each department that adjacent, you calculate the proximity rating based on the value. So in this case, we use this value. You can just change it into 25 maybe, or 65 or something like that, as long as it represents the importance of closeness rating. Okay, in this case, we found out that the L, the locker room and office shouldn't be placed next to each other. However, our layout show that it's placed to each other, so that we have the total evaluation score with the -700, right? It means this current initial layout is not good and we need to redo it. How we can redo that is by doing it all over again from the beginning and choose the different department as the starting point. So either you can choose the probably production area or other, and because the large negative weight associated with the X rating, we need to understand that they shouldn't be placed close to each other. Okay, because if this department can be placed far from another, then the layout score can be how to say maximized. Okay, and in some literature they also mentioned that we can actually have a cutoff value to eliminate some layout, because we should repeat several times, right, due to the randomness for the initial solution, and then from there we can just cut off and eliminate layout that have value less than the cutoff score. How to have this cutoff score is usually the decision maker choose it. Okay, actually that's all for today. So is there any question? Yeah. So I will use the same link over and over. So next time it's okay. I will just share this recording to you also. I hope you can understand. And as I mentioned before, so some of this algorithm actually developed a long time ago, but it's still being used right up until now. And some people actually make the software, and some make the code already, either using Excel or the actual kind of like application. However, while I'm making this material, I try to find one that can be used in my computer, and I didn't get it, at least for the free version. So maybe if you are lucky enough, you can try to find the application, the software on the internet, and maybe you can try to run it to your
Is there a name for the application?
Pardon?
What is the name of the application so we can install
So
it?
it's the same. The name is the same. So Aldep, Craft, Core Lab, it's the same. The name of the application.
Same with the algorithm, yeah?
Yeah. The name is the same.
Oh, I see.
So you can try to find it. I hope you can find it. You can do trial and error using that actually. Probably they will have a limitation because it's quite old. But I think it's still good exercise, yeah. And then if you probably have interest in layout, then you also can use this the app. But I'm not sure because it's quite old, so maybe it's not compatible with the current technology, I think. But maybe we can maybe you can try. Yeah. Is there any other question? Yes. Okay. Good. So it's actually quite easy. Next week will be a bit difficult because it's quite mathematic, but should be easy for you guys. It's okay.
So we will not use software, right, in this class?
No. But I will not teach about the software itself because we already learned about how the software works. So it's the same. Yeah. The algorithm, I already explained the algorithm. The software is the computerized version of this algorithm, right? And if you can find it, that's good. You can try do it by yourself. I think it should be easy. It should be easy. It's not like a simulation where you need to understand and put everything based on the logic. It's just you need to have some need initial solution, some might not need initial solution, something like that. Yeah.
And for the submission of the assignments, only the leader of the group, right?
Yeah.
So we still have 2 classes more, right? If I'm not
Yes.
mistaken.
Yeah. 3 actually.
Third week it will be holiday or not before the exams?
You want to have holiday?
No, I mean from the university, because usually before final
so
term we have 1 week.
so actually the last class should be kind of like you presenting, but as I mentioned, I forgot, did I mention to you or not? You just make the video of you present your final project, and then I will just
Review it, yeah.
yeah. Yes.
So you do
So
record and we send it to you.
yeah. So I will just mark it as a class. Big, because this semester is quite packed. The number of week is not enough to cover all the class, right? Yeah. I think that I think that's kind of win-win solution. You don't need to attend the class, additional class, and I don't. It's easier also for you guys to make a video rather than presenting it live, right?
Yes.
Yeah.
Okay. Do you have any question regarding anything? No.
I think it's clear until now.
Okay. Okay. If there are no more questions, maybe we can end the class. If that's fine with you, I will do the presents manually. Yeah. Is that okay?
All right. Yes.
Okay, thank you so much for attending today's class. I hope you're always healthy and happy. And don't forget about the assignment. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Miss.
Thank you.